This is Voyager Notes, a transmission from 25 billion kilometers, still transmitting. In 1964, a 3.5-Kelvin microwave hiss arrived from every direction in the sky, and nobody at Bell Labs knew what it was. Arno, Penzias and Robert Wilson had been trying to calibrate a large horn antenna in Holmdel, New Jersey. The noise wouldn't leave. It didn't track the sun, it didn't vary with the season, and it came from no identifiable transmitter, on the ground or in orbit. This is what a cosmological frontier sounds like before anyone recognizes it. The horn antenna at Holmdel had been built for satellite communications work. It was large, sensitive, and precisely pointed, qualities that made it useful for detecting faint signals and equally useful, it turned out, for detecting a signal nobody had planned to receive. Penzias and Wilson ran the calibration program carefully. They accounted for every known noise source: atmospheric interference, ground radiation spillover, the thermal contribution of the instrument itself. When they subtracted everything they could account for, a residual remained. Approximately 3.5 Kelvin, isotropic, persistent across months of observation. They checked the antenna physically. There was a pair of pigeons nesting inside the horn, and the team removed them. The droppings were cleaned out, the pigeons returned, the pigeons were removed again. The signal did not change. Loop hash 1 opens here. Why would a signal this uniform, this featureless, arrive identically from the direction of the galactic plane and the direction perpendicular to it? No terrestrial transmitter produces that pattern. No known astronomical object, no star, no galaxy cluster, no known emission nebula produces that pattern. The team had no framework yet to explain what uniform isotropic microwave emission at that temperature would mean cosmologically. That framework existed, but it was sitting in papers nobody at Bell Labs had read. At Princeton, roughly 60 kilometers away, a separate team led by Robert Dick had been constructing an experiment to search for exactly this kind of signal. The theoretical prediction was not new. George Gamow, Ralph Alpha, and Robert Herman had calculated in the 1940s that if the universe had begun in an extremely hot, dense state and expanded and cooled over billions of years, the thermal radiation from that early epoch should still be detectable today, shifted by the expansion of space into the microwave band, arriving uniformly from every direction, carrying a temperature of a few Kelvin. The prediction had largely been forgotten. Dicker's team was in the process of rediscovering it experimentally when Penzias and Wilson called. Penzias and Wilson, 1965, published the detection. The finding is now called the cosmic microwave background. The CMB is not starlight, it's not the glow of galaxies. It's photons that last, scattered off matter when the universe was approximately 380,000 years old, before any star or galaxy existed, at a moment when the plasma that had filled space finally cooled enough to become transparent. Before that moment, light couldn't travel freely. The universe was opaque, a dense fog of charged particles. After that moment, photons decoupled and began their journey outward. The ones arriving at Earth today have been traveling for roughly 13.8 billion years. They carry the temperature of the moment of their release, red-shifted by the expansion of space to the microwave range, landing at approximately 2.7 Kelvin in current measurements. What Penzias and Wilson measured, 3.5 Kelvin, was consistent with that prediction within the precision of their instrument. The slight discrepancy from the current accepted value reflects the calibration limits of the equipment, not an error in the physics. The signal was real, and it was old in a way that required a complete revision of the question being asked. The question had been, what is this noise? After the identification, the question became, what is encoded in it. Loop hash 2 opens here. The CMB arrived isotropic, meaning uniform, meaning the early universe appeared to be the same temperature in every direction to a very high degree, but not perfectly. And the imperfections matter. For decades after the 1964 detection, mapping those temperature variations, fluctuations at the level of 1 part in 100,000 across the sky, became the central project of cosmological observation. The COBE satellite, launched in 1989, produced the first maps. The WMAP mission, launched in 2001, refined them. The Planck satellite, launched in 2009, resolved them to the finest angular scales achievable by a space-based instrument. Each successive measurement returned a signal that was not perfectly smooth. The universe at 380,000 years old had tiny density differences, regions that were very slightly warmer or cooler. Those differences, carried forward by gravity over 13.8 billion years, became the large-scale structure of everything. Galaxy filaments, voids, clusters, the scaffolding of matter across observable space. The 3.5-Kelvin Hissey, Penzias and Wilson couldn't explain in 1964 turned out to be a map of the seeds of structure. The antenna at Holmdel had been aimed without knowing it at the boundary condition for the universe's entire subsequent history. But the map is not complete. The CMB contains a set of features whose explanation still has no single agreed model. Among them, the so-called Hubble tension, a discrepancy between the expansion rate derived from CMB measurements and the expansion rate derived from local distance measurements. The two methods, each refined to high precision, return values that don't agree with each other. No instrument error has been found to explain the gap. No modification to the standard model has fully resolved it. The tension is documented, measured, replicated, and still no clean answer exists for why the two approaches to measuring the same quantity return different numbers. There is also the question of what preceded the CMB. The surface of last scattering, the moment the universe became transparent, is as far back as photons can carry direct information. Before 380,000 years, the universe was opaque to light. Whatever happened in that earlier epoch, the inflationary expansion that is thought to have stretched the universe to near uniformity in its first fraction of a second, the nucleosynthesis that produced the ratio of hydrogen to helium still measured in stars today, none of it is directly visible. It's inferred from what the CMB carries as a record, the way a tree ring carries a record of drought without the drought itself being present. Loop hash 1 pays off. The uniformity that puzzled Penzias and Wilson, the feature that made the signal so strange, because it arrived identically from every direction, is now understood as evidence for a period of extremely rapid early expansion that smoothed the universe before the CMB photons were released. The uniformity isn't a mystery anymore, but the mechanism behind the smoothing, inflation, is still a theoretical framework without a confirmed observational detection of its specific signature. The B-mode polarization pattern in the CMB that would confirm inflationary gravitational waves has been searched for and not definitively found. The Planck mission's final data release identified several large-scale anomalies in the CMB temperature map that don't fit cleanly within the standard cosmological model. One of them, an alignment between the largest scale fluctuation modes and the plane of the solar system, has no accepted physical explanation. It could be a statistical artifact. It could reflect something about foreground emission that hasn't been fully modeled. Nobody knows yet. The 3.5 Kelvin hiss from Holmdel in 1964 became one of the most precisely measured signals in the history of observational science. Penzias and Wilson received the 1978 Nobel Prize in Physics for its detection. What they found opened a frontier that has been mapped with increasing precision across 60 years, and the frontier is still open. The Planck satellite stopped operating in 2013. Its data archive continues to be analyzed. Future CMB experiments designed to measure polarization at finer resolution are proposed or under construction. Each is aimed at a different feature of the same ancient signal, the one that arrives uniformly, persistently, from every direction at approximately 2.7 Kelvin. Loop hash 2 pays off. The small temperature variations that seemed like noise in early measurements became the whole point. The cosmological story is written in differences of 1 part in 100,000, not in the average. The surface of last scattering is a hard horizon. No photon from before 380,000 years can reach Earth directly. Gravitational waves, if detected at the right frequencies, might carry information from earlier epochs. Neutrinos from the early universe are predicted to exist as a background analogous to the CMB, but their detection is beyond current technology. What lies before the CMB is known only by inference, and the inferences still disagree on the details. The Horn antenna at Holmdel, New Jersey is still standing. It was designated a National Historic Landmark in 1989. The signal it first detected is still arriving, a 3.5 Kelvin hiss from every direction, carrying the record of an epoch no instrument can directly see, containing a Hubble tension that 2 different measurement methods confirm and no current model resolves, encoding in its polarization the possibility of a signature that would confirm or refute the mechanism that made the universe smooth enough for structure to form. What came before the surface of last scattering and whether any instrument will ever reach it remains open. The signal is still arriving from every direction. Which detail in the record stays with you?
This was Voyager Notes. The signal is still coming back.